Hello, everyone. Welcome to our deep dive into statistical procedures in environmental geography. Now that we have covered the syllabi, today we are focused on the science of evidence. We are not just calculating numbers, we are building a methodological framework to turn environmental data into actionable insight. So let's begin our journey from data to discovery. So the world is complex, chaotic, and infinite. As geographers, we often start with an I think or a belief or a hypothesis. For example, I think this nutrient cycle is failing. In statistics, the bridge is that to take us from I think to I follow to I know. By creating models and analyzing population rather than just individual points, we find the signal within the noise. So we use statistics to provide the rigid framework we needed to measure chaotic environment system accurately. So to keep our research rigorous, we follow a seven-step roadmap. We divide into three phases. First, plan, then act, and then solve. We start first by formulating a goal and determining our data. Then we move into action, collecting, checking, and presenting data. Finally, we solve the puzzle through analysis and conclusion. If we skip a step, especially the planning phase, the entire structure of your research can collapse. We will walk through these steps today. So first, planning and design. In geography, the question determines the method. So, are you looking at the social economic pattern, like population density and income, or are you looking at spatial geography, analyzing the land use or forest cover? Your planning phase must define the where and how before you ever step into the field. The goal is to ensure that your statistical method accurately matches your geographic site questions. So, where does our evidence come from? We distinguish between population, the whole group, and the sample, the part we actually measure. We also look at sources. Primary data is what we collect yourself in the field, or secondary data that's come from established institutions. Think of BPS or BIG for geospatial data or NASA for a satellite imagery. Knowing your source is the first step in ensuring data credibility. So, not all data created equally. We deal with qualitative data, so like nominal, like type of soils, or ordinal, like low, medium, high risk. Then also quantitative data, so like a interval or ratio scale, which allow for precise mathematical operation. Understanding whether your data is categorical or a measurement is vital because it dictates which statistical test you can use later on. So the third phase, the toolkits. So nature offer comes follow a pattern like a bell shape or a normal distribution. Most data points cluster around the mean. In environmental geography, we rely on the central limit theorem. We'll talk about that later. So this tells us that as our sample grew in size, the distribution of the sample means will look like a bell curve. Even if the underlying population is messy, this is the foundation. Almost all the inferential tests that we will perform later. Okay, Let's discuss for the first case study A, which is an experimental geography in red onion. So the main goals is to see how the difference between fertilizer and PK dosage affect the onion growth. Different dose, different growth. So this is the experience run for 90 days using one onion variety and three treatment groups: half dose, one dose, and double dose. Now to measure growth, we use the leaf length as the indicator. You can see for the half dose only reach about 2.4 centimeters. For one dose showed better growth, and for two dose had the highest growth as around 7.7 centimeters. So the difference is quite clear. Overall, the results show a strong positive relationship between NPK doses and the red union growth. This is only in this example. The more fertilizer given, the better union grew. But as I mentioned, this is only for this examples. Maybe in the next topics, you will see that there is a certain point that giving more will not giving more result, but even worse. So let's go for the next case. Let's focus on aquatic biogeography. So the main questions here is, do different pond lining affect fish growth? The subject of the study is betutu fish. The experiment was conducted 120 days. So we use one fish species, but three different treatment. Or in here is three different pond types: earthen pond, net pond, or tauparin pond. So basically, we compare this, and everything we keep the same, and the only things that change are the container and the pond lining. And we look at the growth based on the weight gain. So we use then ANOVA test whether the difference are statistically significant. The earthen pond as treatment A show the highest average weight gain. It's about 53.86 grams. The net pond is slightly lower, and the tambourine pond has the lowest growth. So the important part here is the superscript letter. The different letters indicate the statistical significance difference, which means the pond type really does affect face growth, and this difference is not caused by a random variation. Look at the table carefully. So, however, we can look at the survival rate. The conclusion a bit different. Visually, it might be looks like that the earthen pond has a higher survival rate, 85%, compared to the others. But statistically, the difference is not significant. So even though the numbers look different, the ANOVA test showed the variance is likely due changes, not the pond type itself. In short, pond lining affect growth, but does not significantly affect survival. We will learn about this later in this course. Okay, so let's move to the next example, case study C. So we look at the urban heat. So basically, cities tends to be hotter than the area surrounding. So on the left, the surface at temperature of night, red means hot, blue means cool, and you see that the city center stand out much hotter. On the right, we have a land covered map. Black areas show developed land, like buildings and roads, and green is vegetation, and yellow is barren land. Now, in geography, we have to be careful. Just because two things happens together, or we call correlation, doesn't mean actually one cause the other. For example, we see that the pave and the concrete are associated with a high temperature. But if we don't just assume that means caution, caution. This where statistic comes in. By analyzing millions of pixels from the satellite data, we can test whether the relationship is statistically significant or not just a coincidence. And the result clearly support that the urban heat island effect showed that developed or the concrete dominated area consistently have higher surface temperature than the vegetated area. We finally arrive to the conclusion. How to draw conclusion from this example. So across all these studies, as you might see, statistical analysis help us move beyond observation and make reliable conclusion in geography. Case study A about the fertilizer, case study B about the fish growth, and case study C about the surface temperature. So in overall, let's see that all these examples show that statistics allow geographers to distinguish real effect from visual pattern and avoid confusion between correlation with causation. So to wrap even things up, based on the fish study, we can clearly say that the container types does affect fish size, and there is a significant difference in weight gain. So yes, the environment matters for growth. However, when it's come to survival, the container type does not make significant difference. Even the numbers low difference, statistically, those differences are likely due changes. So what does it mean in practice? So if our goal is to maximize growth or biomass, then the earthen pound is the best option. But for if your goal is to simply keeping the fish alive, then any container type is statistically acceptable. And when we connect this with other studies, from union to fish and to urban heat, the key takes of the key takeaway is that statistics help geographers make evidence-based decisions, not just rely on what looks different. Statistics is powerful, but it has guardrails. It gives us the probabilities, not 100% absolute certainty. It predicts what group or population do or do not, what a single individual point will do. And finally, garbage in, garbage out. Your conclusion is only as credible as your sampling method and your data quality. So, as a wrap up today, keep these checklists in mind. So, first, is your goal clear? Is your source reliable? Does the sample actually represent the population? If you can answer yes to this, you are on the way to turning data into true geographic insight. You will see you in the next session where we start our first calculation. Thank you.